All right, so that is, here we have water molecules. Water molecules sometimes pass through a channel, but usually when we talk about water, so this is called an aquaporin. I'm sure there are other types of channels as well that move water through, but I just want, this is the funniest little, this is a good introduction to that nomenclature. The nomenclature of proteins is usually pretty straightforward. In this class, when you come across a word that you think, oh God, that's a complicated one, not usually. Actually, almost every word that we come across, I try to remember to do this, simply break it apart into little structures that you know, and then it'll take a lot of the mystery away and maybe a lot of the difficulty of this class, in my opinion. The word aqua means water. Pore means a hole, like a P-O-R-E, a pore. And then that I-N at the end of the word, you may recall, infers that it is a protein. So an aquaporin is a water hole protein. So it's a protein that simply allows water to move from one side to the other. In this case, you can see that there's more water molecules outside of the cell, fewer water molecules inside of the cell, and so the water is going to tend to pass through the aquaporin. And now you'll remember that water is definitely polar. And notice that it's actually passing through that lipid bilayer. That's because it's a small molecule. So it's not going to be able to move through with great efficacy, but it will eventually move through that lipid bilayer and be able to enter the cell simply by dint of the fact that it's a small molecule and able to squeeze between those little phospholipid fatty acid tails. All right, so water will move into areas where the osmolarity, the total concentration of particles in a solution, is greater. A solution that has a solute concentration equal to cellular fluid is an isotonic solution, and cells will show no net gain or loss of water if exposed to this type of solution. But solutions may be more concentrated than cellular fluid if they are hypertonic, or less concentrated than cellular fluid, which would be hypotonic. A cell will have a net gain of water if exposed to a hypotonic solution, or a net loss of water if exposed to a hypertonic solution. Let me show you how this works. Here we have our friend the red blood cell, which remember isn't a cell at all, but we use it for this purpose because it has such a distinctive shape to it. It's got kind of that biconcave, sort of that dip, sort of like an incomplete donut. In an isotonic solution, so the root iso means same, hyper means greater than, hypo means lesser than. In the case of osmosis, water moves in the direction where it is going to be moving into the direction where a solute or a salt is highly concentrated. So it's worth spending a little bit of time on this one here. An isotonic solution, which means same tonicity or the same concentration inside of the cell or outside of the cell. What will happen is you'll have water moving equally into and out of the cell. There's no net change here because you always have water leaving, you always have water entering, and this is actually how the human body must exist. It exists at a 0.9 molar concentration in the cells and outside of the cells, also known as 300 milliosmoles. We'll be talking about all that way towards the end of the second semester of the class. Super, super important because what happens, everything exists at this same salt concentration. Not to say that everything is exactly the same, but the concentration, like the gross concentration of everything is going to be at 0.9, this 300 milliosmoles. Because this is what happens when something goes wrong with that. So in a hypertonic solution, what this means is that the cell is in a solution that is highly salty, for example. So hyper meaning greater than, tonicity. It's got the solution surrounding this guy has a bunch of salts in it. And as a result, the water is going to move into the direction of the highest salt concentration. Now this is a little bit tricky to understand, especially if you're kind of struggling a little bit with diffusion. I focused on the idea that diffusion is solutes moving from high to low concentration. Here we're saying water moves into an area where the solutes are concentrated. So it's kind of like diffusion in reverse. It's like the water is doing the job because the solutes cannot move easily wherever they're supposed to be going. So if you have lots of salts outside of the cell, the net result is that water will leave the cell and pass into the area where there are more salts. And as a result, the cell will actually start to shrink and collapse in on itself. The opposite will happen if your cells are in a hypotonic solution. Hypo meaning less than, tonicity, lower concentration. Now, inside of the cell, it's still at where it's supposed to be, like 0.9, 300 milliosmoles, whatever. But outside of the cell, there's a great deal of water and fewer salts. And as a result, water will have a net movement into the cell, causing the cell probably not to burst per se, but it will certainly enlarge and it will not have the functionality that it had before. This might potentially happen when a person is highly hydrated, for example, really, really hydrated. When we talk about kidney physiology in second semester, we'll talk about specific instances of this, but it's possible to drown yourself from the inside if you drink absolute boatloads of water. And we'll talk about very specific situations. It's unlikely that if you're just trying to hydrate by drinking lots of water in a day, that this is going to happen to you. We're talking about massive amounts of water, very specific situations. The opposite is true if a person is very, very dehydrated. This type of a thing might happen. Or possibly if a person has been toxified by a great deal of salt in their diet. Again, not just a salty diet, but poisoned by sodium, for example. Hypernatremia, it would be called. All right, so I think that's what I wanted to say about passive transport. Simple diffusion, make sure you understand how that can work. And this would be usually something where molecules can simply move down their concentration gradient without much fighting against, like passing easily through a membrane or simply passing through a beaker where there's no membrane to block their movement. Facilitated diffusion is usually going to require a protein or some kind of a structure because those particular molecules need a little bit of help to get across, like if you're polar and you're trying to get across a non-polar membrane. And then lastly, osmosis, where water moves through a membrane in the direction of a high concentration of a solute. Those are all passive.